Okay, we want to investigate an interesting geometric problem, and that's given any two lines in three-dimensional space, as shown in this diagram. What I want to find is the closest approach that those lines have to each other. I want to find not only what their closest separation is at their closest point, but I also want to find the points on the two lines that form that closest separation. So really what I'm looking for is something like this. Here I have two lines. There's the blue line and the red line. And I want to find the line that connects them just like this, where that is the line representing, or the line segment representing their closest approach. So how do I go about finding that line and these points here and here that represent the points on the blue line and the red line where their approach is the closest? Okay, well, to begin that discussion, let's suppose we have any point at all in 3 space. And here I've shown this green point sitting in space right there. And that just represents any point. And if I want to find the closest approach of that green point to, let's say, the blue line, what I want to do is I want to go to the green point and I want to draw the line that comes in perpendicular to the blue line. Okay? Any other line I draw to the blue line, which is not perpendicular to the blue line, is a longer line. It's like the hypotenuse in this right triangle from there to there and back. Okay? Do you see that and understand that? So in this case, a line, something that goes from here to something like that, will represent the closest approach of the green point to the blue line. Similarly, same thing on the red line. Here, if I want the closest distance of the green point to the red line, I would draw a perpendicular that would go something like this to there. So we see, in fact, it is a theorem in geometry that if we have any point in 3 space, the closest approach that that point makes to any line is in the perpendicular distance to that line. Okay, so we want to use that piece of information as follows. Suppose I have any point that's on the blue line, any point at all on the blue line. Let's say this point right in here. So if I'm at this point right in here, I want to find the point, how is this point, or the distance from this point at its closest to the red line. And I would drop the perpendicular down to the red line. It would look something like that right here, right? So here I'm looking down the blue line. For any point down the blue line, you can imagine that the closest point would be something like the perpendicular would look like that perpendicular dropped. So from here to there, something like that. So if I have any point on the blue line, and I say I want to find the closest that that line is to the red line, it's going to be the perpendicular from that point to the red line. So let's suppose I happen to have the point on the blue line that is the closest to the red line. Now I don't know exactly where it is, but let's suppose I had it. Then I would draw the perpendicular from that line to the red line. Okay, and I know that that perpendicular is the closest of any line I can draw to the red line. So that perpendicular line must be the line that represents the closest distance between the two lines. Now suppose though I'm at that point on the red line where that perpendicular intersects the red line. And I ask the reverse question. I want to draw the line from that point to the blue line. Okay, and the line from that point to the blue line, which represents the closest, the shortest distance to the blue line, is the perpendicular from that point to the blue line. Now, so what I have is I have the 2 points on the red line and the blue line, which are closest to each other, and I've just made the argument that the line connecting those 2 points must be perpendicular to both the red line and to the blue line. Okay, so keep that in mind now, and let's go back to the line that I had drawn here, the white line, which I have already computed that in fact represents the closest approach of the two lines. And you can see that is true, that this white line is in fact perpendicular to the blue line and it's perpendicular to the red line. Okay, so you can see that that's true. Now, how do I go about computing that white line? Well, what I want to do is I want to find the direction that is perpendicular to both lines. In other words, let's say I want to find, if I imagine that I have a vector in the direction of the blue line and a vector in direction of the red line, and I want to find a vector that is perpendicular to both of those vectors, I can do it by doing the cross product of the two vectors. So this is exactly what I do. I can use the direction cosines from the equation of the blue line to give me a representation of one vector. For example, here, right here, here I have the equation of the blue line, and I have the three direction cosines as being 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. And so I can use that then as a unit vector, which is in the direction of the blue line. Similarly, if I go to the red line here, I have the red line has these direction cosines, 1 over the square root of 2, negative 1 over the square root of 2, and 0. So I now have the coordinates of one vector with each, which is perpendicular to the blue line and to the red line. Now with that, then I take the cross product of those two vectors. Now if I do that, okay, what I get is, and I want to take the cross product, and then after I take the cross product, I want to make sure that I have a vector which is only of unit length. So if I take the cross product of two vectors parallel to the red line and the blue line, and I don't get a vector which is a unit length, I want to make sure and convert that into a unit length vector. So I take the cross product of a vector parallel to the blue line and a vector parallel to the red line, turn it into a unit vector if it's not already, and if I do that, I'll get this vector noted in white right here. See that vector in white? Okay, that is a unit vector which is perpendicular to both the red line and the blue line, which I found by using the cross product. Okay, now suppose that I have any point on the blue line and the red line, any point whatsoever. Let's say I have a point on the blue line here and a point on the red line there, and I draw the line between the blue line and the red line. Okay, there's nothing special. This just has to be any one point on the blue line and one point on the red line. Now what I'm going to do is draw a vector which represents that direction of this vector. So I'm going to draw that vector, but I'm going to draw the vector coming out of the origin. So it's coming out of the origin just like this white unit vector is coming out of the origin. So this is what I get. So you can see those two vectors, those two lines are parallel to each other. Okay, but here I have the unit vector perpendicular to red and blue, and I have this vector which I've gotten just by drawing a line between any 2 points in the red line and the blue line. So now I use the dot product. If I do the dot product between the purple vector and the white unit vector, what that will give me is the projected length of the purple vector onto the white unit vector. Okay, so I do that dot product, and I get this vector right in here. Now, if you think about this vector right in here, which is the projected length of the purple vector onto the white unit vector, that vector right in there must in fact be the direction, have the direction and length of the line that separates the blue line from the red line at their closest approach. So that vector right here is the same as the vector represented by this length in this direction. So I now know what the distance is between the blue line and the red line at their closest approach, and I know what the slopes, the direction cosines are for that line. What I don't know yet is I don't know where the point is where it intersects the blue line and where the point is that it intersects the red line. Okay, so in order to find that, okay, what I do is I take this white vector. Now let me show you what I do. Is I take this white vector right here and I just bring it up and I add it to, I take my equation for the red line and I add this white vector to every point on the red line. So when I do that, it looks just like I have it shown here. Here's the red line. Here's the white vector add there. But I add it to every point on the red line. And then I imagine that I slide that white vector right along the red line here. As I do that, I'm drawing another line right over here, which is exactly that distance away. So I end up with a line that looks something like that. So this is what I get. I add the white vector coming here, which represents the distance between the blue line and red line at their closest approach. And I add it to the red vector, and I slide it across, and that gives me this vector right here, or this line right here, the orange line. Now all I have to do then is I have the equation for this line, because I've taken this and added to that. I have the equation now for this line, so I have to find where this line intersects the blue line. And where it intersects the blue line, it represents the point on the blue line, which is the closest approach to the red line. So when I have the coordinates of this point, I can then work, knowing this direction and this length, I can then find the coordinates of where the point intersects the red line, and I have my answer. This then gives me the location of this point, the location of this point on the blue line and the red line, and I also have the direction and distance of their closest approach. So that's how I do this.